some of the basic properties of self-adjoint operators. Okay. I hope that you already know what's a self-adjoint operator. It's like an operator whose adjoint is itself. We call them as self-adjoint operators, and these operators are pretty much important in many different areas, and especially in PDE theory. That if your operator turns out to be a self-adjoint operator, you must celebrate it because we have lots of results to solve PDEs. PDEs actually. Let me quickly begin with recalling some of the basic notions. Imagine I have an operator from norm the space E into F, then a number lambda from the field K is called the eigenvalue. Okay, it's called eigenvalue if what happens. So it's like when you operate A and F, and it turns out that you are getting F as an output, but a scaled version of it actually. Okay. So in other words, those functions or those values, those inputs, which are invariant, okay, under A in the sense of direction actually, okay, are roughly invariant under A because lambda can be negative as well. You call A is invariant under A, so F is invariant under A, but the only size goes up and down actually. So it's a scaled version of the same vector you get as an output actually. Then the ratio by which this F is being scaled, you call that as an eigenvalue, and the F can have a specific name. And what would be that name? So that would be the eigenvector actually. And what would be the eigenspace, associated eigenspace? So it's going to be the kernel of lambda I minus A. Okay. And if this kernel is non-trivial, what does it mean? It means that there are some eigenvalues. Okay. And it's not necessary that, as we know in the matrix theory, so it's like a very analog version of. So what you do in the matrix theory, you're just repeating it for the operators actually, obviously in infinite dimension. So you call such values an eigenvalues, and you call this as an eigenspace. So if this is non-trivial, that means that there are some eigenvalues and hence eigenvectors actually. So what would be the relationship between eigenvector and this eigenspace? Any relationship that you know is that these eigenvectors, which are corresponding to the eigenvalue lambda, you can have multiple lambdas and hence multiple eigenvectors. So these vectors span this subspace actually. Okay, so these eigenvectors are roughly, what do you call, bases for this, what do you call, eigenspace actually. Okay, so we all know this is stuff, so there is no need to get much into that. The next thing that I would like to define is not eigenvalue, but an approximate eigenvalue. Okay? Approximate eigenvalues. What is the interpretation of eigenvalues? What are applications? You know all actually. So like one of the applications that we saw, a very serious application, was Google Page Rank actually. So eigenvalues are making our life easier actually. Okay? So whenever you are using Google, say thanks to the eigenvalues. Okay? Because this Google Page Rank algorithm is based on what we call essentially this notion of eigenvalues and eigenvectors. So what do you mean by an approximate eigenvalue? So imagine that I have an operator A which is linear and bounded from E into E, and I have a lambda in the field K, and this lambda is called approximate eigenvalue if this happens. if I can find a sequence Fn in E, so it's like if there exists a sequence Fn in E, okay, such that the norms of these sequence is unit, okay, it's like, okay, each term of the sequence has a unit norm, for all n in n, and a Fn minus lambda Fn goes to 0 as n goes to infinity. Okay? I mean, if you see, this is a pretty much a strong condition. It's a very strong condition. Okay? While this one is a weaker condition. So you don't require them exactly to be equal. Okay? While if they are equal somehow, so if there is a sequence with a unit norm such that, so it's like you have this equality roughly, but not in general, but in the terms of norm actually, okay, then you call such values as an roughly, what do you call, an approximate eigenvalue. It's not really an eigenvalue, but an approximate eigenvalue.
So why this unit norm is necessary?
I mean,
Fn the norm है वो 1 होना चाहिए.
I mean, if we don't have this, then we're gonna face lots of trouble. We're gonna see some results, and then this will be mystified that why you need it. Okay. One of the thing.
What's E?
Huh?
E क्या है हमारे पास?
So E is a normed space. Okay. So
Operators.
Yes, it's just the E is a normed space, and it is a linear bounded operator from E to E. Okay. So if you have a bounded operator and you can find such a sequence for which these two things holds, then everything is fine. Okay. This would be much easier to do in Hilbert space. Just think about it. If the E is Hilbert space, then what would be this Fn's actually, which can make my life easy. So this could be the orthonormal basis. Think about it. So if you have orthonormal basis which have such a property, and for the orthonormal basis, it's not necessary that for the orthonormal basis you have this inequality, but if you can have this, then so in other words, like in Hilbert spaces, this is a much easier way to achieve what do you call the approximate eigenvalue. So what would be an example? Okay. So an example of approximate eigenvalue could be do what? Okay, what would be, before getting that, let me talk about an example here actually. So, okay, you can have finally lots of operators for which you have eigenvalues, but I'm giving you an operator which has no eigenvalues actually. What you need to do, just take H to be, or maybe E to be L2 0 to 1, okay, and take A as an operator from H to H, which is nothing but a multiplication operator, okay. So A F operated onto T is simply giving me T times F of T, okay, and my claim is that this multiplication operator, A has no eigenvalue. Why this would be the case? Think about it. A has no eigenvalues. Why this would be the case? Because if I just think about it, I can give you a hint that if you have, so what you want AF to be equal to lambda F, and you want a solution of this problem actually. So does this, so are there such lambdas for which this must be true? Then what? So this is going to be, so it's like if I operate these both things on the t, okay, so you're gonna get t f of t times lambda times t f of t, okay, and what are you gonna get? You're gonna get t minus lambda times f of t equal to 0. What would be your next conclusion? Huh?
Either t is lambda or f is.
So either t is lambda and f is 0, but since f is arbitrary, okay, then t is lambda. In other words,
T is equal to lambda. T is another constant number.
so you have different choices actually. Okay, either this, like in product both components are 0, each one of component is 0. So my point is this, and think carefully about it, that why each of the choice, okay, is not going to make sense actually. You can't take t to be lambda, lambda to be t. You can't take f of t to be 0. Here is the example, okay. So I'm saying that take h to be the same space L2 0 to 1, okay, and take operator A to be what? T f of t, the multiplication operator.
Yes, sir.
And your claim is, my claim is that any lambda naught in 0 to 1 is an approximate eigenvalue of what? Of A, this multiplication. Okay. So what would be proof of this? So in order to prove this, what you need actually essentially, if you go back to definition, you want a sequence with a norm 1.
No.
Okay, and you want, this convergence actually, that a fn must converge to lambda fn in the norm of e as n goes to infinity. So this is what that you essentially want. So I'm saying that consider this fn, okay.